Welcome to a proof exercise in which we are given the statement for all integers a and b. If a plus b is even, then a and b are even. We're asked to determine the contrapositive, converse, and negation of the given statement, then determine whether the original statement, the contrapositive, converse, and negation are true or false, and then provide a proof. Let's go ahead and get started. For the implication if a plus b is even, then a and b are even, let's let P be the statement a plus b is even and Q be the statement a and b are even. For part A, we're asked to write the contrapositive of the statement. For the implication if P then Q, the contrapositive is if not Q, then not P. When writing the contrapositive, we need to be careful about negating the statement a and b are even. We need to apply De Morgan's law, where the negation of P and Q is logically equivalent to not P or not Q. When negating Q, the and changes to or. The negation of Q is A is not even, or B is not even, or we can shorten that to A or B is not even. The contrapositive is for all integers A and B, if A or B is not even, then A plus B is not even. Notice the quantifiers for all integers A and B does not change. Next, we're asked to write the converse. For the implication if P then Q, the converse is if Q then P. The converse is for all integers a and b. If a and b are even, then a plus b is even. Notice how here we just interchanged the hypothesis and conclusion. Part C, we're asked to write the negation. We need to be careful when negating the statement. When we negate the statement with the quantifier type is going to change. Looking at the notes below, the negation of for every x, p of x is logically equivalent to there exists x such that the negation of p of x. So when the negation passes the quantifier type changes, which means in our case, when we negate the statement, for all integers a and b will change to there exists integers a and b, and then we have to negate the implication. And the negation of if p then q is logically equivalent to p and not q. The negation of the statement is there exists integers a and b such that a and b is even and a or b is not even. So again, the quantifier changed, and then we have p and the negation of q. For part D, is the original statement true or false? Provide a proof. And again, the original statement is for all integers a and b, if a plus b is even, then a and b are even. This statement is actually false because we can easily find two integers that are not even and the sum is even. For example, if a equals 3 and b equals 5, a plus b is equal to 8, which is even, but a and b are not even. Remember, examples can't be used to show something is true unless we have an existential statement, but we can use examples to prove a statement is false. For a more formal proof that this is false, suppose a plus b is equal to 8, which is even. Let a equal 3 and b equal 5. A plus b is equal to 3 plus 5, which is 8. However, a and b are not even. The statement for all integers a and b, if a plus b is even, then a and b are even, is false. Part E, is the contrapositive true or false? Provide a proof. From before, the contrapositive is the statement for all integers a and b, if a or b is not even, then a plus b is not even. We should recognize this as false because remember, the contrapositive is logically equivalent to the original implication or the original statement, which we already proved was false. We can prove the contrapositive is false by using a direct proof. Assume a and b are not even, meaning odd. Let a equal 2x plus 1 and b equal 2y plus 1 for some integers x and y. A plus b is equal to 2x plus 1 plus 2y plus 1, which we can write as 2 times the quantity x plus y plus 1. Since a plus b is a multiple of 2, a plus b is even, however, a plus b are odd. Therefore, it is false that if a or b is not even, then a plus b is not even. For part F is the converse of the original statement, true or false. The converse is the statement for all integers a and b. If a and b are even, then a plus b is even. We should recognize this as true. If we add two even numbers, the sum is also going to be even. We can prove this using a direct proof. Assume a and b are even, that a equal 2x and b equal 2y for some integers x and y. a plus b is equal to 2x plus 2y, which can be factored as 2 times the quantity x plus y. Since a plus b is a multiple of 2, a plus b is even. Therefore, if a plus b is even, then a plus b is even, and the proof is complete. And for the last part, part G, is the negation of the original statement true or false provide a proof. And again, the negation is there exist integers a and b such that a plus b is even and a or b is not even. We know the negation is true since the original statement is false. Because we have an existential statement, we can use proof by example. We just need to show there exist two integers a and b such that a plus b is even and a or b or both are not even. Let a equal 3 and b equal 5, a plus b is equal to 8, which is even, and a and b are not even. This proves there exist integers a and b such that a plus b is even and a or b is not even. Remember, a or b is not even is still true when both are not even, which is the example that we used. I hope you found this helpful.